Right, so maybe we can get started. All right, so good morning, everyone. It's a great pleasure to have Jonas Peters today in your summer school. Jonas is a professor of statistics at the University of Copenhagen. Previously, he was a group leader at the Max Planck Institute and a postdoc at ETH Zurich. He studied mathematics at the University of Heidelberg and the University of Cambridge, and did his PhD both at the MPI Tübingen and ETH Zurich. And Jonas has done a lot of work in statistical methods for causal inference, and is co-author of a very famous book now on this topic, Elements of Causal Inference. And welcome, Jonas, to the school. So the floor is yours.
Thanks a lot for the kind words, and thanks a lot for the introduction. So good morning, everybody. It's a pleasure to be able to speak here. It's really a great program, I think, that is put together, and I'm really looking forward to this tutorial. The first thing I would like to know whether all of you can hear me and the sound is working fine. So maybe we can just do a small warm-up exercise, and everyone can just very quickly write in the chat if he or she feels comfortable with this, where you are planning to do your holidays, or maybe you already did some holidays, and you can just write down what you did. So I will also write something. You did a bike trip in Denmark. Jutland, great to hear. Okay, so this seems to be working. Portugal, I see a lot. Nice, it's also nice. Okay, thanks for this. It seems like the sound is working. So what I'm going to do, I'm going to talk about causality, and I prepared a couple of slides, and we will have a few practical sessions in between. So this means that I'm cutting down a bit the theoretical part, and I decided, I'm warning you already, I decided to leave some of the slides in so that you could have a look at them later. So I marked slides that I'm going to skip. I marked them with a yellow background. So I will skip them during the talk because they are not completely necessary, but if you happen to be interested in more details, just have a look at the slides afterwards, and then you can also go through the yellow slides. I hope they make sense. And if not, feel always free to contact me if you have questions. Then of course you can use the Slack channel also in the coming days. There may be two more announcements. So we will have breakout sessions for this practical part, and there we will stop the streaming as far as I understood. So this means that you don't have to be worried about being recorded or streamed with any questions that you have. Also, I will have a couple of visual breaks in the talk. So these are just random pictures that I'm going to show. And this is mainly for reminding myself that we have little breaks where you can ask questions. So please do ask questions and interrupt at any time. This can really be as interactive as you like. And I prepared, as I said, several slides, but I don't have to go through all of them. So these are the small announcements that I wanted to do. Good, let me share the screen and then we get started. Okay, so I'm going to talk about causality. And this is the first disclaimer. So there's really a lot of work going into this tutorial, and I very much try to include the important references, but apologies if there are some that are missing. We are, of course, a bit more thorough with this in our book. There will be also a link to that later in the slides. And also, there are in causality, so we're going to see what causal models are in the first part, and there are different ways of formulating causal models. And these different languages, if you like, they have some advantages and disadvantages. And it's so I won't say that one of them is just better than the other, So it's really worth looking into all of them. But of course, for time reasons and for my personal experience, I'm focusing on one of them. These are structural causal models today. But there are other frameworks, maybe you've heard about the potential outcomes, that are also very useful in some aspects. And this is not going to be covered in this talk. Also, what I'm not talking about today is statistics, or at least relatively little. That means, okay, but how efficient, for example, can we estimate certain quantities? It's also an important part of the topic that I'm skipping. So in this sense, the presentation will be biased. Okay, so what do we need causality for? This is an example that I like. This is a made-up example where you have two data sets where we are measuring the activity of a gene. Think about gene expression level on the x-axis and a certain phenotype. So think about flowering time or something on the y-axis. And now what we are very much used to in machine learning and statistics is to model the joint distribution. So these, we see a sample here, the red dots. Why? Because then you can answer questions like, well, what is the expected value of the phenotype, given that you observe that the activity of gene A, let's say, is 2. And then you can, sort of, if you have a model for the joint distribution, you can just compute this. In causality, however, we are often interested in a different type of questions, namely in interventional questions. So what is this? So you could ask, what is the expected value of the phenotype, or the best prediction of the phenotype, if we intervene on gene A and let's say we even delete it? So this means that we are actively setting the activity of gene A to 0, and we are asking what is the best prediction for the phenotype now. And this is a very different nature of a question. It becomes relevant in many situations. I'm trying to give some examples at least during the talk. And it requires a very different way of thinking. And now I'm just giving an intuitive example why causality is so important to answer this question. So imagine that you have two data sets that really look, from the observational distribution, that look almost the same. So the left picture is for gene A and the right picture is for gene B, but the underlying causal structure is different. So we're going to formalize this. This is just for intuition. But imagine that in the left case, we have the gene A is really causal for the phenotype. So what would this mean? If we are now deleting gene A, so we are intervening on it, we are setting the activity to 0, then we would also expect that the phenotype goes down. So this is here a prediction interval that you see on the left-hand side. Whereas if the causal structure is different, so let's say we have what is called a confounder or a hidden common cause that is causally influencing both the gene B and the phenotype at the same time, then the result is very different, because now if we intervene on gene B and set the activity to 0, then what would we expect the phenotype to do? Well, we would say nothing, right? It does what it usually does. And this means it lies in this area. So again, this is a prediction interval. So this now, why do I like this? Because it says, if you are interested in answering these interventional questions, you have to talk about causality. There's no other way. So of course we can say we are never interested in these kind of interventional questions, and that's maybe also fine. Personally, I think they are important in many aspects of our lives, and in the natural sciences, for example. But if you want to talk about them, you have to talk about causality. And now this is what we are going to do in the first pass, formalize a bit what a causal model is. Just as a sort of a small point, of course, in reality, I mean, we have been looking at data that is very similar to this, the gene expression data, but we have also been looking at other real-world data sets, and they can be, of course, much more complex. So this is a recent example where we're looking at the dependence and, of course, the causal relationship we are trying to infer between violent conflicts and deforestation in Colombia. So what you see here now, I hope it's visible, is a map of Colombia. And in the color grading, you see the forest loss, and the red dots are violent conflicts. This is accumulated over time between 2001 and 2017. And now the question is, what is the influence from violent conflicts on deforestation? There's a lot of debate. There are positive and negative effects, and the question is whether we can infer something from the data. And again, now you have something like certainly a confounder that you see on the right hand side. So this is, for example, population density, because of course only in populated areas there will be conflicts, and also only in populated areas there will be deforestation. So now we have a situation similar to the above. So the question is, what can we do about confounders? But I'm also showing this example because the data structure in real life is often much more complex. So here we have spatial data, we have temporal structures. So it's not really this classical IID setting. But I'm mostly skipping this for this talk due to time reasons. But I think it's quite an interesting area to look at. Okay, this is another example that became very famous. So maybe some of you have already seen it. This is an example with kidney stones. So you have two different treatments, treatment A and treatment B. And what you see on the in the table here are the recovery numbers. So here 350 patients were treated with treatment A and 350 patients with treatment B. And now you just look at the recovery rates and it looks like treatment B is better. So 83% versus 78. Now, why is this data set famous? Because you can actually split these patients into two classes with small stones and large stones. And now the picture changes. So this is at first sight a bit weird. Why? Because if you now look at the small stone category, it's that treatment A is better than treatment B. So 93 versus 87. And also for large stones, it's better, 73 versus 69. So I give you a few seconds to think about what could have happened here. So intuitively, this is the reason is that the causal structure is maybe slightly more complex than we would initially think. Why? So if you think about it, and if you look at the numbers closely, you realize that treatment A, so the large stones are somewhat the more difficult cases, maybe also not surprisingly. So here the recovery rates in total are smaller than the recovery rates for small stones. And what happened here is that somehow one could say it's an unfair comparison because treatment A had to deal with many more of the difficult cases. So here this is 263 versus 87, and on the treatment B it's 80 versus 270. So it's many more of the difficult cases that treatment A had to deal with. So therefore the overall recovery rate is smaller. We can make this more precise. So we can now draw a causal graph. So the size of the stone is causing the recovery. Large stones are more difficult. And also the size of the stone is causing the treatment. And this is because of background knowledge. We know how this data set was created. And then the treatment has an effect on the recovery. And again, we have this confounding effect from the size of the stone. And we are interested, so if you want to say which one is better, you can argue, well, I'm really interested in this causal effect here from treatment to recovery. And what we are going to see that it's actually quite easy to compute these effects from the overall distribution if you know about the causal structure. So what is the expected recovery if all get treatment A? This is a typical interventional question. So you say treatment should be independent of size of the stone, so you intervene on treatment. This is what we're going to compute. Okay, so now we're going into the meat, if you like. So this is on an abstract level what I think, and I believe many others as well, about the causal models. So what we are very much used to is that a statistical model. So think about you have a multivariate Gaussian with a certain covariance matrix that is parameterized. This is a model for an observation for a joint distribution. We call this here P. A causal model, however, is something stronger. It should be able to do more than that, because it should be able not only to model the observational distribution, but it should also be able to model what happens under an intervention. So what happens if I intervene on the treatment, for example, or if I delete this gene. So it models at the same time this observational distribution and a lot of interventional distributions. And these you can denote by this famous do notation, what we're going to see in a minute. You can also say that it outputs a causal graph. So some people do this differently, but I like to think about it this way. Just think about the graph as being a representation of the underlying causal model. And then you can also consider counterfactuals, but I'm not going to do that today. It's a fun topic though. Okay, so part one, what is a causal model? And you're going to see that this is a surprisingly simple thing, I hope. Here's an example, and this is an example where we are looking at two random variables. So let's say the altitude of a place. So we have been looking at data from Germany. So think about not a very flat country, but also not the Himalayas. And the temperature, so the average temperature at this place, average yearly temperature. Now, these are two random variables, and we have measurements of at different locations. And now we are thinking about writing down a model. And here I'm going to write down, or I've been written down a causal model for this. So how does it look like? A structural causal model, SCM, now contains of different things. So the first thing is there are different assignments. So here, these are two assignments for the two random variables we are interested in, X and Y. And they depend on these N variables, and these are noise variables. Think about error terms. Now, X is just NX, and Y is minus 6 times X plus NY. So this is this minus 6 is not, I mean, it's not totally out of the blue. Why? Because if you increase the altitude, then the temperature goes down. And if you measure this in I think 1,000 meters, then this is roughly what you expect. Now, the second part of a structural causal model is that you specify the noise distributions. And here I'm just saying, well, let's assume they are IID, and they're both Gaussian 0, 1. Now, clearly, this is not the most sensible model at all. Why? Because a Gaussian distribution for in particular the height or the altitude and the temperature doesn't make a lot of sense. So you could think about something smarter there. But it's this is important for me. This is just the model, right? I'm not claiming that we are describing the truth or anything, or this is exactly the truth. I'm just writing down a mathematical model for my observations. And of course, someone else can have a better model. But the first step we need to understand is how these models actually work. Now, this model here induces an observational distribution. And if you think about it, I'm convinced that all of you could come up with it. Why? So look at, for example, first X. Well, we have that it's a Gaussian distribution 0, 1. Now you can look at the mean, for example, of Y. Well, this is minus 6 times X, so its mean is still 0 plus NY, the mean is still 0. And then because everything is linear, also this is certainly the joint distribution is a Gaussian distribution. So it's a multivariate Gaussian distribution. The means is 0. This is what we just looked at. And you can look at the variances and covariances as well. And this is on the bottom here, this is what you get. So it's a multivariate Gaussian. This is the observational distribution. So this was this first link that I drew. And now the question is, well, what about the interventional distributions? And now this is sort of as easy as it gets, because why? So in intervention, we can now represent by just replacing one of the assignments. So think about a computer code where you generate X and Y, for example. And then this is just one line in your computer code. So if you want to generate one observation from the observational distribution, what you could do is you could just sample the observations from the noise distribution at the beginning, and then just use these lines here in your computer code. And now you are intervening on a variable by replacing one of these assignments. Let's look at an example. So if you now, this is of course hypothetical, but if you now increase the altitude of the place that I am at the moment, which is in North Zealand in Denmark, to 3,000 meters, then what we would say is, well, we're just intervening on X, we are setting it to 3, and the other part of the causal model remains the same. So this is the Y assignment here. This remains the same. And the reasoning now is to say, well, you're trying to, this is already, I think, hinting at something very useful, because you're changing only a part of the system. The remaining parts remain the same, and you can think about different, let's say, physical relationships. So here, the relationship between altitude, temperature, is, you can think about this as a physical one. So you would think that maybe it remains intact. But this is how we represent an intervention. What is the effect? Well, the effect is that the induced distribution now is different. It's certainly not Gaussian anymore, because x is 3. This is deterministic. So what do we get? We get that the probability that x equals 3 is 1. So x is always 3, right? This is a deterministic relation. So think about your computer code. X is always set to 3. And y is still a Gaussian distribution. Now with minus 18 as a mean and the variance 1, details don't matter. But what is important here is that the distribution changed. And because it's a different distribution, we would like to give it a different name. And this is where the do notation comes in. So we just call it p, and now we give it a subscript. We just say do x equals 3. And this do reminds us that we have replaced an assignment. So we are really setting it. This is why Judea Pearl came up with this do notation. It's really a very active thing to do. Important here, think about this as being just a different distribution. You could also call it Q or R or whatever. It's just this do notation is a very useful name, because it reminds you how you generated it. I should say that you can, of course, always ask things in between. However, unfortunately, I don't see the chat. So maybe Pedro or someone can, if there are urgent questions, or if you think that there is something useful, just interrupt me at any time. I don't feel offended at all. Good, but we will have a break, a small break in a minute. Now, what you can also do, not surprisingly, you can, of course, also intervene on the other variables. So this is now even more bizarre, maybe. So you can set the temperature at a place to a certain value. We put it under a glass dome or something. And then we are replacing the y. So again, what we have yet another distribution. It's a very different one, and we give it a different name. Now, observe two things that are already intuitive, hopefully. So the first thing is, by intervening on y, we are changing the causal graph, because we don't have this edge between x and y anymore. So now we have set y to some value. It can be a random value, right? And therefore this link is gone. The other observation here is that the marginal distribution of x remains the same. It's still a Gaussian distribution with mean 0 and variance 1. It didn't change whether we intervened on y or not. And this is giving you a hint that actually, or this is a formal way of defining that y does not have a causal influence on x, because if you intervene on it, it doesn't change. It's a bit of a tricky thing, but this is a first order approximation. Okay, this is it. So you can do this with more than 2 variables, but this is really a structural causal model. You have a number of random variables that you can see here on the left-hand side, x1 to x4. These are the things that we would like to model. And then you have these assignments where you always have a function of some other variables and some noise variables that we here call n. Then you have to specify a joint distribution over the n's. So we say, let's say they are jointly independent, Gaussian 0, 1. And then what you can do is you can draw the graph. How do we draw the graph? You already guessed it, I think. We just draw an edge from a variable that appears on the right-hand side to the variable that appears on the left-hand side. So here, for example, you see an edge from x1 to x2, because x1 is on the right-hand side of the assignment of x2. x4 has two what we call parents, so two incoming edges, x2 and x3, because these two variables appear on the right-hand side. So it's a bit different from maybe what you've heard about graphical models, in the sense that we are using graphs really as a representation of a structure rather than the model itself. The model itself, personally, I think about the structural causal model. To make our lives easier, we are assuming for this talk that this graph has no directed cycles. Of course, in reality, you want to relax this, and you can do that. Why does it make things easier? Because without cycles, you have always a distribution that is induced by the structural causal model. It's a unique one. And with cycles, one has to be a bit more careful, because you can imagine if, let's say, x is 2 times y plus some noise and y is 2 times x plus some noise, it's a bit unclear what kind of distribution I'm describing, because it seems like a system that is somehow exploding. So one has to be a bit more careful, but of course this can be done, but not in this talk today. Again, the story is the same. So you're using a joint distribution. So now I'm not asking you to compute it. I did this for you. This is just a big covariance matrix. This is our observational distribution, which we call P. And at the same time, you can also intervene. So you can set, for example, x1 to 0, and then we are ending up with an interventional distribution that is called P do x1 being 0. Very importantly, sort of the last comment here, this is not the same as conditioning. So one tends to think this sometimes, but it's very different. So setting x1 to 0 is very different than conditioning to x1 being 0. And I'm trying to explain this. I go back one slide. Imagine that x1 is 0. So if you condition on x1 being 0 in the observational distribution P, this tells you something about the value of x3, right? So if this x1 is 0, it cannot be that x3 is 1000. So in a way, it's like, if you like, this is a bit of Bayesian way of thinking. So conditioning on x1 being 0 means you can update your belief about x3. And then this tells you something about the value of x4, for example. However, if we intervene, it's the next one, then we cannot do this. So if we intervene and set x1 to 0, you don't know anything about x3.
And this is... Jonas, can I interrupt? Sorry, we have a question from a student from Zwoyun, asking if you could go back to the two variable example, just to explain why. He's asking why applying do y equal to a normal distribution doesn't change the joint probability. That's his question.
It doesn't change the, could you repeat that?
The joint probability.
Ah, okay, very good question. Maybe I said something wrong here. So what I meant to say is, it does not change the marginal distribution of x. So of course, right. A very good question. Of course, it does change the joint distribution of x and y. Of course it does, because we are even generating something that is independent, right? So if we intervene on y, what you get, it's this slide, what you get are two variables that are now completely independent, because we are randomizing, if you like, we are setting y to a random value, and x is some random value, and they don't depend on each other. So we are indeed changing the joint distribution, but what I wanted to say is that we are not changing the marginal distribution of x.
Okay.
Yeah, this does not change.
Thank you.
Yeah, but good question. Good. So this is really the structural causal model. There's not much to it. So what is the concepts are relatively simple. They are, of course, I should say, there are a couple of technical issues. If you're a big fan of measure theory, you can look at a few details, because one has to sometimes be a bit careful. So what does it mean that the variable appears on the right-hand side and so on? But these I really regard as technicalities. This can all be dealt with. What is a bit confusing at the beginning maybe is that one really has now an object that one usually doesn't study in statistics or machine learning, because it generates, it's some sort of a meta construction, right? So because we are generating so many different distributions at the same time. Back to the example of the kidney stones. So how could we write it? Well, we just say we have the treatment. This is a function of size of the stone and some randomness, some noise. We have the recovery, that is a function of the treatment, size of the stone, and some noise. And we have the size of the stone, that, let's say, that is just a random function. And again, this is a model, right? And it's this time a causal model, because it also answers what would happen if we intervene on something. And now, so this is a scenario where you are writing down a causal model, and maybe we don't know yet sort of what these functions are and what the distributions of the noises are. So we can parameterize this and try to learn this from data. So this works as before, but then what we end up with is a causal model that gives rise to these interventional distributions. Now, what is the question that we want to answer? We want to say, what is the expected recovery if we, let's say, intervene and everyone gets treatment A? So now we have a formal way of writing this. So we are interested in computing the probability do t equals A, this is the intervention, and maybe then we are interested in computing the probability that recovery equals 1. Now what I would like to show you is one principle that is I only realized, I think, in the last, I don't know, last couple of years, that is really at the fundamentals of this causal way of thinking. And this is something that the econometricians actually already understood quite well in the 40s. And this is the concept of modularity or autonomy or invariance. So what do I mean? If you are intervening on the treatment, you're really, I mean, you're not replacing these assignments for the other variables. And this means that a lot of these mechanisms remain exactly the same. And this looks a bit innocent, but it's actually, it's really the key concept here. And it does make sense in many situations. So if you think about randomizing treatment, we actually, at least we hope, right? So I'm going to talk about this in a minute. If you have placebo treatments as well and so on, we hope that by the treatment itself, you're not changing the physical system of the body. So you're changing some parts, but other parts remain the same. So here, it's like by changing the treatment, you're assuming that the recovery functions the same way, in the following sense, that this assignment here remains the same. And this means, if you think about it, this assignment really specifies the conditional distribution of recovery given treatment and size of the stone. So this conditional distribution is completely determined by this assignment here. And the fact that this conditional distribution remains the same even after an intervention, this is sometimes called modularity or autonomy. And this is quite important. So I'll try to give this a name. So if you intervene only on XJ, you intervene only on XJ. I like to call this mute because I claim this is the most useful tautology ever. So you're more than welcome to challenge me to find a tautology that is even more useful. But this is a pretty useful one, and we are going to see a couple of applications of this this morning. This is, again, the data, and now there's a lot of things on the slides, but I really want to only highlight this autonomy once more. So this is the data that we have seen from this kidney stones data. And now, I mean, it's a simple example, but I hope it carries the message. This is the data that we have. We have observational data from a situation that is on the left-hand side. Apologies. This is the distribution P. Now, we are interested in a distribution that is different in an interventional distribution. Do treatment equals A. And now one could ask, well, but these are two different distributions. So how am I ever going to sort of infer something about the distribution on the right-hand side from data or the distribution on the left-hand side? And this autonomy is the key trick. Why? Because in these two different distributions, as I just tried to argue, we have this, because of this autonomy principle, we have that the conditional distribution of R given S and T remains the same. So this means that in the black distribution, this conditional is the same as in the orange distribution. And this is because if we intervene on the treatment, we are only changing the treatment. We are not changing the other mechanisms. And this is the key trick why we can actually compute quantities in this world by just using data or the observational distribution from the left-hand side. And I'm not going to show you the precise details. I'm just going to, I have a slide here and you can look at this later if you like. This is really the thing that what we are interested in, to compute the expected recovery under this interventional distribution. And then you just massage the formulas. And at the most important step, what you're doing is you are replacing sort of the interventional distribution by the non-interventional distribution, because you're looking at the conditional distribution. And then what you are able to do, you can look at this later if you like, you can compute the expected recovery under this interventional distribution. And this is in some sense, it's quite nice, right? Because when you see this example first, you would think that maybe the doctors did a stupid thing by just assigning the difficult cases to the treatment A. Why did they do this, by the way? Because they already thought, I mean, treatment A is the more severe treatment also, but they already thought that treatment A is better than treatment B. So this was their way of thinking. And often the first response is, well, the doctors did a stupid thing. They should have randomized the treatment. Then we wouldn't have had this problem anyhow. But in some sense, you can also argue, well, but we can still compute, if we know exactly how this procedure was done, right? We can still compute the interventional distributions afterwards. And maybe the way we collected the data was actually better for the patients. This is all a bit simplifying, but hopefully this makes sense. Otherwise, of course, please ask. So what if you do this, what you get up as a result is really that the expected recovery under do treatment equals A is 83%, whereas the expected recovery under treatment B is 78%. So this is, if you like, the formal answer to the question, which treatment is better. So if you intervene and the expected recovery is better under treatment A than treatment B. And the key concept here is really this modularity. This is from the first part, maybe the most technical slides, because it is a formula that looks a bit weird. But this is the adjustment formula. So what do I mean? So here, intuitively, what happened between the recovery and the treatment? The problem was somehow that it was confounded. This effect was confounded by the size of the stone. And the computation that I have on the last slide, this actually you can do much more generally. We're saying you have to adjust for these confounding effects in order to compute the causal effect. So what does this mean, adjustment? We are just defining this formally right now. Assume that you have a structural causal model over X and Y and W, and you're interested somehow in the causal effect from X to Y. So what does this mean? We are interested in the left-hand side of this equation. We are interested in the, let's say, density of Y in an intervention where we set the variable X to X. So this is intuitively looking at the effect from X to Y. Now we call a set Z a valid adjustment set if we can actually compute this interventional distribution, if you like, by an adjustment, so-called adjustment formula. What is the adjustment formula? It's just the thing on the right-hand side where, and this is important now, you have quantities only from the observational distribution. So this is similar to before, where we wanted to compute an interventional effect from the treatment by just using the observational data. And here, this is how the formula looks like. You can look at this later. The precise form doesn't matter that much, but it's important that this only involves the quantity P, not the quantity P do something, because this is where we may have the data from. So this is if this holds, then this is a valid adjustment set. So now, of course, the obvious question is, well, how do we ever figure out whether something is a valid adjustment set? And this you can just read off from the graph. And one important example is the parent adjustment. So whenever you are using the parents of X, not Y, by the way, the parents of X, then this is a valid adjustment set for XY. Let's rethink about this kidney stone example. X is treatment, Y is recovery. And now we are adjusting for the parents of X without the, so the parents of X, so this is the parents of the treatment, and this is just size of the stone. So here, size of the stone is indeed a valid adjustment set. And it's a bit funny that the proof really, I mean, you have different ways of writing it, but you can write it such that it really depends only on this autonomy example. I like to talk about one special case and then a class of examples. So the special case is in particular if the empty set is a valid adjustment set. So then this means you don't have to adjust for anything. So then what you can just do, then you have actually that the interventional distribution is the conditional distribution. But this is really rare because usually you have this confounding effect. And in general, you have that the interventional distribution is not the same as the conditional. It's just here for the protocol.
Jonas,
yeah,
there's another question here from Massier. Asking about the kidneys example, asking, don't we have to account, so we don't have to account for the fact that cases assigned to treatment A were more suitable for this treatment, especially if doctors assign treatment based on their expert knowledge?
Yeah, very good point. That's a very good question. So here we are assuming that the doctors only assigned the treatment by knowing the size of the stone and nothing else. But it's a good point. And here it's again what I would like to stress maybe once more. I mean, there's this idea. I mean, you have heard, for example, all models are wrong and some are useful. And Popper, for example, would say that you need to falsify models if you need to be able to falsify models if they should be scientifically relevant. And these ideas, I think, are very important to keep in mind. So I'm writing down a causal model, and this I can write down as an SCM, as I did in the kidney stones example. And you should always, of course, question this model because it makes some assumptions. And this question that you're pointing out, which is a very good one, it points exactly at this, right? Because we are saying, well, there's nothing else that confounds the treatment and the recovery, whereas in practice there might be. So in practice, indeed, if the doctor looks at some other measurements of the patient, then there might be very well another confounder. And this is often in reality, you have to sit down with the practitioner and really talk about these things. And so now I'm saying something, hopefully it's not confusing. It's particularly helpful, particularly important in causal inference, I think. Why? Because imagine that you have a model misspecification in you have a computer vision application or something, and you're trying to detect whether there's a lion in the picture or not. Now, if you have a model misspecification, in some sense, it's not a big problem because you can always do some cross-validation scheme, and you can hold out some data and you can just check how well am I performing on this holdout data. And now, if you're performing very well, in some sense, you think, well, I don't care about my model misspecification because it works very well in the task that I'm looking at. In causality, you cannot really do something like this because if you have a sort of a misspecified model, think about what are we trying to do, right? We are trying to predict what would happen on an intervention. And often we don't have interventional data. So we cannot sort of check whether we are doing good, but holding out some parts of the data. But we just have to trust the outcome. And in particular in these situations, it's very important that we talk a lot about the model. Formulating it differently, you can also say, and this is what I think, in many situations, it's really good to have at least a bit of interventional data, because this will tell you whether your model assumption is completely off or not. And sometimes,
I guess maybe even in a regular machine learning application, the lion example will be sensitive to the distribution shifts. Like if something changes from the validation set to the real life application.
I fully agree. And this is also, I mean, I don't know whether I have time at the end, but this is something that we are also looking at. I think it's quite an interesting topic where you see that this is one of the things where maybe machine learning can benefit something from these causal ideas, because this is what in causality happens all the time. You're always talking about distributional shifts. Yeah, thanks for the question.
There's yet another one from André Martins, just asking if the kidneys example is an instance of the Simpsons paradox.
Yeah, it is.
Yeah, I think Yuda Pearl on the book of why he says that causality kind of sheds light on this paradox. Like I don't,
Well,
maybe
maybe I'm not sure whether I understood this, but I think actually, so I see this, if I understood correctly, I see this differently. So I think the paradox, it's really not a paradox. It's just writing down the causal model, and then there's no paradox left. So I think
okay.
so I would say the causality really dissolves the paradox, because it's just I mean, everything is consistent in this example. I write down a causal model, and then I just have, I mean, what is the paradox here? I can compute the interventional distributions, and it's just that the observational distributions, the observational conditionals, they have a different order than the interventional conditionals, if you like. But there's nothing that tells me that they shouldn't have.
Yeah. I guess maybe without the causal graph, the paradox would be that treatment A is B for all cases, but treatment treatment B is better for all cases, but treatment A is better for each case, right?
Yes, but
if there's not causality.
Yeah, but I would argue that, so why would this be, right? And I don't, so I would even maybe go a step further. I would say it's even impossible to resolve this paradox without talking about causality. But I think if you talk about causality, it's really the case that, well, if you think about it, right, treatment A had to deal with all the difficult cases. So this is all, I mean, it is the causal explanation of this paradox, I would say.
Mm-hmm.
But maybe that's a great discussion for later, or the Slack channel.
Sure, yeah. Sure. Okay, thank you. These were the questions for now.
Good. I'll just have a quick look at the time. So just as an example, what I wanted to talk about this adjustment, because it looks very abstract and so on, and very general. It becomes a bit more concrete in linear Gaussian models. And I just wanted to briefly talk about this example to explain once more what this adjustment is doing. Think about a graph like this. So it's a complicated graph, and let's say everything is linear in Gauss, and we are interested in the causal effect from X to Y. So here again, we are given the graph, right? So later we will look at situations where we maybe want to infer the graph or learn the graph, but here we are given the graph. Now we want to infer the causal effect from X to Y. And if you just think about in a linear Gaussian case, you can regress. So you can, for example, regress y on X and look at the regression coefficient. Now, this is in some sense not giving the right causal parameter. Why not? Because we have this confounding path. This is the red one that I drew. This is sometimes called a backdoor path because it enters the X through the backdoor. So this is somehow messing up the dependence between X and Y. So we are interested in the causal effect, and this is represented really only by these two edges. So if you intervene on X, right, then the effect somehow propagates through the graph, and we see an increase of the expected value of Y, let's say. So we are really interested in only sort of trying to estimate the effect of this path, but if you just regress Y on X, we also have a mix of these two different paths, the black one here and the red one. And this sort of messing things up. And this is where adjustment comes in. So the backdoor, the parent adjustment tells us that the C and A is a valid adjustment set. These are the parents of X. So what does this mean in practice? In practice, this means that if you regress Y not only on X, but if you regress Y on X, on C and on A, then we are getting actually a coefficient that really represents only this causal path here. So let me just put numbers here. So if you think about this is a linear equation, right? So D is minus 2 times X plus something. Y is minus 1 times D plus something else. Then what we are interested in is we are interested in this causal effect here. So if you intervene on X, and if you increase it by 1 unit, then the expected value of Y will increase by 2 units. So it's 2 times X. So we are multiplying these two numbers. And if you just, so the number 2, this is what we are looking for. But if you just regress Y on X, you don't get the 2 in front of the X as a regression coefficient. You get something wrong, or something inconsistent, we would say. So now, but if you use this adjustment formula, then if you regress y on x and c and a, then in front of the x, you will get something that is very close to 2. So this is how this adjustment formula, I mean, it's not difficult math, you can do it, but this is how it translates to the linear Gaussian setting. And now C and A are not the only valid adjustment sets. You can also do something else. For example, you can just adjust by K. I'm not proving this here, I'm just stating this. You have to believe me, but of course it can be proven, but we only saw the parent adjustment on the slide before. This is only the first case. But I can tell you also K works, for example. So if you regress Y on X and K, you also get something that is very close to X. If you regress something like on F, C and K and X, it also works. Not a coincidence, because I'm a big supporter of the FC Köln. So I needed to get the abbreviation FCK somewhere into the examples. Okay, so these are adjustment sets. And what is important now is, and this is maybe the take-home message here, you cannot just throw in any variable. And this is what you sometimes see in, of course not always, but sometimes you see this in applied papers, where you're trying to estimate a causal effect by a regression. And then people are thinking, okay, we just throw in all the variables that are somehow related to the problem in order to adjust for these confounding effects. And this is wrong. So here, if you throw in the variables K or C and A, then this works, you get something consistent. But for example, if you add the variable G, in this case, you get something inconsistent. So the question is really, do I have a valid adjustment set or not? And not just throw in as many variables as you like. And the general, this has been studied quite a bit. So the general rules are known for deciding whether something is a valid adjustment set or not. And then, of course, you can start doing statistics. This is also what people have done, thinking about, okay, what are the statistically most efficient adjustment sets and so on. But it's important that if you include some variables into the regression, you get a consistent estimate. These are exactly the valid adjustment sets. And for others, you get the inconsistent estimate. You can try this out, and I'm adding some code later. This is one comment. This is maybe now a bit for the experts here. Don't worry if this doesn't make sense. It's not needed for the rest. So again, if you do a regression in R, this is LMY, you regress on X and K. This yields a consistent estimate of the causal effect. And I was just always now saying causal effect, this is a number plus 2. What is this causal effect, right? We always talked about the interventional distribution. So formally, this sometimes you summarize an interventional distribution by the left-hand side here. So we are looking at the interventional distribution. We are looking at the expected value of y, and then we are just seeing how quickly does the expected value of y differ if I change x. So you're looking at the derivative of the expected value of y. And this is this number 2 that comes out. If you like, this is a bit in the Jupyter notebook. You can play with this. Good. This is some code that you can try out. It's just, you can also make this yourself, where you just regress on different sets and you actually see, okay, indeed, for some sets I get a correct value and for some sets I don't. This is something that you observe and practice. This is quite important. So think if you have a problem where you're interested in a causal effect, try to write down the causal graph, and then you need to decide which variables to include in the regression. And here, do not simply throw in as many variables as possible. This is sometimes what you see. Okay, this is my first visual break. I think we had already a couple of questions. Of course, if there are more, I'm happy.
If there's time for one more, I'd like to ask one myself.
Yeah.
In the example with the various valid adjustment sets,
yeah,
maybe 2 slides ago, why is A alone not a valid adjustment set? Why do we need to adjust for C as well?
Oh, A would work as well.
A would work. Okay.
Yeah, I didn't list. I'm sorry, I didn't list all of them.
Okay, you wrote C and A because they're both parents, right?
Yeah. So the thing is that the parents using the parents always works. The parents of X always works. Okay. But in addition, there may be other variables that work, other sets that work. Yeah.
Okay.
There's a general theory. I only wrote down the parent adjustment set, but we also write something in the book about if you're interested in a general formula for when a set is a valid adjustment set. There's a formal criterion for this. And you are, I mean, we are just citing the papers. This is not work by ourselves. But your intuition is correct, because I'm pretty sure, because you're saying you can just use A, right? Because we are blocking this path here. This is the important part. You somehow have to block this path, and the C doesn't do anything.
Yeah, that's.
And then, I mean, maybe one more point for the intuition. Why is G problematic? So you are also not allowed to open other paths. So you need
it will get some of the effect of X on Y, right? If we
yeah, exactly. Yeah.
If we adjust for G.
Yeah, thanks. Good question.
Okay, thank you.
Good. Then, I mean, just maybe two more historical points that you may have heard about. I think they're quite interesting. So the question of randomization, how does this fit into the picture? And here, this is just a historical history that became important. James Lind was a Scottish medical doctor, and the problem of scurvy was quite large in the 18th century. I think this in the book *Sapiens*, there's also a story where they actually claim, the author claims that the solution of the problem of scurvy was one of the reasons why Great Britain became such a big empire. But of course, this is a historical claim, so it's hard to validate. But what was the problem there? So a lot of people suffered from scurvy, died on the boats. So then the question is, well, maybe the foods, the nutrition has something to do with the recovery or the prevention of scurvy. And here we have the same problem. So it could be confounded, right? So the status, it could be that only the captains had like the good foods and they recovered, but they only recovered because they had the better bed. So you don't know whether it's really the food or not. So this is the typical confounding problem. And now this is, I think, really a genius idea. So if you think about big statistical ideas, I think this is one of the top ones in my personal hit list. This is the idea of randomization. Because if we now intervene on food and we set it to a random value, this is what you can call a randomization. What are you doing, right? So you're replacing this this mechanism for food, and now formally in the graph, because you're replacing food by something random, so let's say the outcome of throwing a die, you're destroying all the incoming edges. So what does this mean? So this means now several things, right? So intuitively, this means whenever we now find a dependence between food and recovery, it must be a causal link. We can even make this more formal, because remember, we don't have to adjust for anything, because now the parents in this randomization experiment, there are no parents of F. F is just random, there are no parents, so the empty set is a valid adjustment set. Or another way of looking at this, there's no path, no confounding path. So the only path between F and R is really a causal path. So this is a genius idea, and James Lind is sometimes said as having come up with one of the first ones. I mean, it's not really a randomized experiment, but still it's quite funny. I think we can read the quote together. On the 20th of May in 1747, I selected 12 patients in the scurvy on board the Salisbury. Trouve ordered each of a quart of a cider a day. So these are all, by the way, these are acids, because they thought they can solve it with acids. Two others took 25 drops of elixir vitriol. I think this was sulfuric acid, if I remember correctly, so they were less likely. Two others took 2 spoonfuls of vinegar 3 times a day. 2 of the worst patients were put on a course of seawater. Also not very pleasant, I guess. 2 others had each 2 oranges and 1 lemon. Aha! Given them every day. The 2 remaining patients took an electuary recommended by a surgeon. The consequence was that the most sudden and visible good effects were perceived from the use of oranges and lemons. And this is, I think, an interesting point here, because back then, we know, of course, now that it's vitamin C that is important. Back then, they didn't know the concept of vitamin C. But this is a model. This is, if you like, they came up with an interventional model, and they realized, okay, it took many decades, by the way, until they really adopted this strategy, but they realized if you have citrus fruits on the board, you're not suffering from scurvy that much anymore. And what I like about this is that you can actually have a causal model that tells you it's the outcome of interventions that you're trying to predict, it doesn't necessarily mean that if we fully understand the full causal path in between, or what's happening, or we don't have a physical understanding necessarily. We have this sort of this actionable understanding of the world, where we're saying, okay, what is the outcome of interventions? And in some scenarios, this is not good enough, because sometimes we really need to understand what are the physical laws tying these things together. But sometimes it's totally sufficient to know this which action we want to do. I think this is a nice way of thinking about different sort of hierarchies of levels as well, where you have a physical model which you might argue is even higher than a causal model. Okay, and just one last story, because it was so famous, of course, is the smoking and lung cancer thing. It's actually a nice paper from 1950. I was a bit surprised when I read this for the first time. It's very well done. What is the problem there? You have smoking and lung cancer, and you saw that there's a dependence. What they did in this paper, they tried to correct for many different things. It can be confounded, right, by gender, by age, by status, whatsoever, and they try to correct for all of these things. They try to adjust for it. The problem is, you could think that, well, don't bother about adjustment, just randomize. But this, of course, here doesn't work, because it's unethical. You cannot say you should smoke, you should not smoke, you should smoke. This would be scientifically, if you're interested in the causal model, this would be maybe the easiest thing to do. But you cannot do this for several reasons. So they came up with, they thought, okay, we just adjust for everything that we can think of. And they always found the dependence. And now, maybe you've heard this before, the tobacco industry, there were some people getting really rich advising the tobacco industry, because what they did is they said, no, you adjusted for all these things, but we believe there's a different confounder. And they came up with this idea that there's a genetic factor that is influencing the desire for smoking and the probability of getting lung cancer. And why is this genius? It's genius because you cannot adjust for it, because back then you couldn't measure the gene expression. So they are saying, well, no, there's a dependence, but this is not causal, but there's just a genetic factor influencing both. So you need to adjust for this genetic factor, but you cannot, because you cannot measure it. So this was one of the debates. And then, of course, people at some point just got the physical understanding, and a couple of other tricks that could be done. But this was the debate back then, and hopefully it now fits very well into this framework of causal models. Nice book if you want to read about these stories, is Merchants of Doubt. Okay, so wrapping up this chapter here on causal models. This is again coming back maybe to this idea of what is actually a model in our machine learning world. So here, if you have just a probabilistic model, so let's say you're modeling a process with a multivariate Gaussian, and you're saying it has this covariance matrix, I can actually try to falsify your model by just looking at data. And if I can do a test for Gaussianity, or I can check whether it's the right covariance structure. If you have a causal model, you can actually falsify it using similar techniques for the observational distribution, but we can also falsify it by interventional experiments. And this could be, for example, randomized experiments. So maybe it helps to think about, I'm not going to use this notation later, but maybe it helps to think about these two causal models as either being probabilistically equivalent. So this means they are inducing the same observational distribution, or interventionally equivalent. This means that they are entailing the same observational and interventional distribution. And now, next, we are going to talk about causal discovery. So we are trying to learn causal models from observational data. And there, of course, the problem is that there are many causal models that are observationally equivalent, but interventionally different. And then, of course, the question is, how can we resolve this problem? But this is maybe helpful when thinking about these models. And this is the last comment here. So in a scenario like this, where we are maybe interested again in this is the toy model for smoking and lung cancer. So in the effect from smoking to lung cancer, where we have a confounding factor that is hidden. This is the notation H here. So this means that we don't observe data from it. Then this is sort of this is a scenario where we would say, well, we don't know what to do, right? Because we would need to adjust for age. This is important, right? But we don't have data from age, so we cannot plug it into the formula. So what shall we do? And this is one famous technique that you may have heard about. These are instrumental variables that work here. So this is in a scenario where you have a linear relationship between smoking and lung cancer. It can be extended, but in the simplest scenario, it's linear. And then you have this instrumental variable, and here this could be text. So what is an instrumental variable? This is an instrument, it's a variable that influences the treatment. So here the smoking, and it doesn't influence the effect directly. So it doesn't influence the lung cancer except for through the path in smoking. And this is, of course, a strong assumption. But if you have this, you can actually identify this alpha. So if you like, there's no valid adjustment set, so we can be sad because age, it would include age, but we cannot use age. We don't have the data for it. So Chuck Norris uses instrumental variables. And this technique I just wanted to mention. And if you like, there now, so we will now do a couple of breakout sessions, and you can have a look at the Jupyter notebooks. And one of them is about these instrumental variables, walks you through how this can be done. So if you're interested in learning about this. Good, this summarizes the first part. So it's really causal models have the ability to model observational distributions and interventional distributions. So you can say, if you're only interested in observational data, forget about causality. It's a first order approximation. But if you are interested in interventions, we really need to talk about causal models. And these are the ones that we discussed, structural causal models. So you have these assignments on the left-hand side. They can be represented by the graph on the right-hand side. And then an intervention is just a replacement of an assignment. Now, the adjustment, this is really, so what is, again, the problem we are trying to solve? If you are given the graph and an observational distribution, you can actually compute these interventional distributions. And one of the notebooks, this compute interventions, is looking at this again, where you can just walk through some of the slightly easier examples. And the instrumental variables, I didn't talk much about this, but this may help if they are hidden variables, so you cannot adjust for them. And there's also one notebook about this. In both of the notebooks, I would recommend you that you skip the first exercise. It's a bit theoretical. You can look at it later, but I wouldn't do it now. And one more comment on in the first notebook, there's one exercise on deseparation. So I'm not 100% sure whether you did this in the summer school already, or maybe some of you have known this from before. But feel free to just skip this exercise as well. So it's a useful concept. It's also explained in the Jupyter notebook. You can either try to go through the definition and try to do the exercise, but you can also skip it. Good. So this is a good place to stop. I will stop the share. What I would propose now to do is we come up with the breakout sessions. I propose groups of 4. And now it's, of course, up to you. But what you can do is you can also discuss a bit what you've heard, if you like. But you can also try to work on these Jupyter notebooks. And maybe one way of doing is that one person for whom the notebooks already run, because installing is quite a bit of work, can share the screen. And then you can sort of try to go through it together. Okay, are there any questions about the breakout sessions? No? Then I would say that we just start them now. And there is if I remember correctly, there's a break at 11:30. Of course, you can feel free to continue working on the notebooks if you like. Otherwise, you just take the break. And then I would recommend we reconvene it after the break. I'm in the different time zone, of course. The break is at 10:30, and then we just reconvene after the break at 11. Okay. Good. Then I would propose that we stop the recording and then create the breakout sessions.